Okay, moving into chapter 7 now. Oops, chapter 7, which is called Analytic Trigonometry. So let me explain what we're going to be going over in this chapter, what kind of the, the point is and the motivation of this chapter. So chapter 5, we discussed, what did we discuss? We basically discussed right angle trigonometry, because we didn't exactly get to the law of sines and law of cosines, which allows us to expand beyond that. But we basically talked about triangles. Oh, hang on. My camera is out of focus. One second. All right. Fix that. All right, there we go. Nope. Oh, okay, there we go. So chapter 5 was basically like trigonometry for triangles. Basically trigonometry for triangles. And chapter 6 was graphical representations, right? Well, chapter 6 was moving to, we moved to that unit circle approach where we graphed angles on the unit circle, which were equal to their arc lengths, and we saw that the trig functions yielded the we could relate them to coordinate points on the XY plane by taking that unit circle approach. And then we moved into graphing the trig functions. Now in chapter 7, titled Analytic Trigonometry, we're going to be looking at basically the goal of this section is going to be to, oh my God, why is this camera doing this to me? Sorry, I wish it's... Okay, we will solve trigonometric equations. We will solve trigonometric equations. I think it might be because it's too bright and the whiteness of it is making it lose focus, maybe. Anyways, so that's gonna be the goal of this chapter. We're gonna solve trig equations. So equations that instead of like x squared plus x plus 2 equals 0, we're gonna solve things like sine squared plus maybe like 2 sine theta plus 3, something like that, equals 0. So some equation that involves trig functions. That's going to be the goal of this chapter. How to solve, right? So we're going to take some baby steps to get there. First step is going to be section 7.1. Section 7.1, which is called trigonometric identities. This is a fun section, trigonometric identities. Okay. So I didn't say this up here, but basically this chapter 5 can be summed up as sort of triangle trigonometry. Chapter 6 can be summed up as graphical trigonometry, and then here this is like algebraic. Basically we're doing like algebra, like the stuff we did in pre-calculus algebra to solve equations there, except now they're trig equations. But first we got to look at some identities. Section 6.1, looking at identities that involve the trig functions. All right, so what is an identity? Let me get set up here. Let me, oh, there we go. An identity is an equation that is true for all values of whatever variable is involved in the equation, or variables, so I'll say of the variables. So we already know, and I'm putting that S in parentheses because it could just be one variable, which pretty much everything we're going to deal with here is going to just be one variable. The variable that we're going to use is going to be theta, but it could be more than one. So we already know some trig identities. We know that, what do we know? What kind of trig identities do we know? We know that secant of theta. So note that my domain variable now is going back to theta, and I'm just following along in the, oh wait, hang on. Let me see what the text is using, because I thought I was following along in the text. Nope, they're using x still. Okay, so I'm going to use x. So secant of x is equal to 1 over cosine of x, and that's true for all x, so that's an identity. We have a few more of these. Cosecant of x is equal to 1 over sine of x, and we have that cotangent of x is equal to 1 over tangent of x. And there is one more sort of relating the functions back to the base functions of sine and cosine, which are kind of like our anchor in this trig stuff, sine and cosine, right? And that is that tangent of x is equal to sine over cosine, sine x over cosine. So note that using that, I can rewrite this cotangent one as 1 over tangent. Well, 1 over tangent is going to be, so here, let me make a note of this. I'm going to start over right here. Cotangent of x is equal to 1 over tangent of x. One of the themes of this section is going to be to get things written in terms of sines and cosines, which is what I'm doing here. I'm writing this definition here of cotangent in terms of sines and cosines, and then cleaning it up. And what do I do when I do 1 divided by a fraction? So remember that this is 1 divided by sine of x over cosine of x. But remember your fraction division rules. That's the same as 1 multiplied by the reciprocal, the multiplicative inverse of the second function. Long story short, it flips it, right? Cosine x over sine x. So hopefully that makes sense to you. You're seeing that tangent is sine over cosine. Cotangent is the reciprocal of tangent, so we should expect it to flip, cosine over sine. I mean, I went the long way there, but if it makes sense to you that I'm just flipping them, tangent, cotangent, because they're reciprocals of each other, then that's good. That's good. All right. What other identities do we have? What other identities do we have? We have the Pythagorean identities. The identities I just listed, you could call the reciprocal identities because they're all dealing with the reciprocals. Not so much tangent, right? But I guess, you know, you can stuff it in there. But we can name these the reciprocal identities. That's how the book names them all. And I mean, of course, it makes sense to call most of these reciprocal identities because they involve reciprocals. This one, not so much. It sort of does. It involves the reciprocal of cosine, but also a sine. So anyways, we're going to call all these reciprocal identities. And now the Pythagorean identities, if you recall the Pythagorean identity for just the sides of a right triangle, we have this relationship, the legs of the triangle square, the sum of the squares of the legs of the triangle is equal to the square of the hypotenuse. Square of the hypotenuse. Hang on, what is my camera doing? Is it moving? Or is it just because I have my screen split? Okay, I think we're good. All right, so what was I doing here? I'm going to derive the Pythagorean identities, which I've shown you them. You may not remember because it was kind of brief and we haven't done anything with them yet. But let me draw a triangle here with angle x and hypotenuse 1. Then what is, now think about chapter 5, right? Doing some triangle stuff here. What is the side measure over here in terms of sines or cosines? Well, it's sine yields, sine of x is going to yield opposite over hypotenuse, right? So let me write this down, sine of x. I'm going to say OPP for opposite, and then hypotenuse here is just 1. So sine of x is equal to the opposite side, right? So that means I can just write sine of x here. So on a triangle with a right, oh, this is a right triangle. Let me make sure that's clear. This is a right triangle. On a right triangle with hypotenuse 1, when you're solving for the legs, it's literally just going to be the trig functions. We'll see it here. Cosine of x, by definition in a triangle, in a right triangle, is adjacent over hypotenuse. But again, the hypotenuse is 1 here, so cosine of x just being is directly equal to the length of this leg here. Okay. Now, can you write the Pythagorean theorem in terms of these legs? Yeah. Sine, how do I write it? Sine squared of x, that's leg 1 squared, plus cosine squared of x is equal to hypotenuse squared, but what's 1 squared? Just 1. There's the classic Pythagorean theorem. I mean, Pythagorean identity. Sorry, this is the Pythagorean theorem. I mean, it's just a special case of it. But anyways, this is the Pythagorean theorem, and this is called the Pythagorean identity. And actually, there's more than one Pythagorean identity, but they're really coming from. This is like the classic base case here. Okay, so what if I wanted to build the other ones, because you know there are 2 others, or maybe if you've forgotten, that's okay, but I'm about to show you there are 2 others. I could build different triangles, right? Let's see, is that going to be what I want to do here? Okay, let's see. There's a couple ways to get it. We could just work from this formula to build them, or we could build a new triangle. Thinking. Should have tried this beforehand. Well, I'll just go ahead and tell you the way I remember that. Like if I ever forget the other Pythagorean identities, here's what I do. I mean, I was going to try and work through another triangle example, and it can be done that way. But if I'm just being like honest, the way I remember the other ones is like this. I remember that, well, if I can divide all of these by cosine squared, all of these terms by cosine squared. Why would I ever want to do that? Well, because I know that that's going to yield a new identity here in terms of secants and tangents. And there's going to be another one that involves cosecants and cotangents. So that's what I'm trying to get to here. Now, what is sine squared over cosine squared? Well, I know that sine over cosine is tangent, and both of them are squared. So technically, what can I do here? Like, what's technically going on with that algebra? This is the same as sine over cosine all squared, right? Because if they're both squared, both of these things are squared, I can pull the square outside of the division here, no problem. So this is just this left-hand term is just tangent squared. Oh, let me see, I'm going to write it in orange. That's going to be my identity color here. So this is just tangent squared of x. By the way, the next term is just a 1, right? Cosine over cosine, or cosine squared over cosine squared, rather. And then here I have 1 over cosine squared, but by a similar argument to what I did over here, 1 over cosine squared is just going to be secant squared. Okay, so there's the second Pythagorean identity coming from the construction of this first one and then building the second one here. And now you can probably guess how I'm going to build the third one. I'm going to start with the base case, sine squared x plus cosine squared x equals 1. I'm going to divide everything by sine squared. Oops, I didn't mean to put a plus there. Sine squared. And this is going to give me a new identity in terms of cotangents and cosecants. So you have an identity in terms of sines and cosines, an identity in terms of tangents and secants, and now an identity relating cotangents and cosecants. So first of all, the first term is easy. Sine squared over sine squared is just 1. Second term, recall that cosine over sine is cotangent, and they're both squared here. Since they're both squared, I can pull that square out, and that just becomes cotangent squared. Similarly here, I can pull a square off of both of these because the 1 doesn't care if you square it, right? So pull a square off of those. 1 over sine is cosecant, whole thing is squared, so cosecant squared of x. So there's that third Pythagorean identity. These are listed in the text as well in a nice table. All these identities I'm building in section 7.1. There we go. There is the 3 Pythagorean identities. First one coming straight from just an application of the Pythagorean theorem on a right triangle of hypotenuse length 1. And then the second 2 just coming from manipulating that initial Pythagorean identity. And notice that they're different, right? The 1 is in a different place on these, right? So don't just think, oh, it's always just like something squared plus something squared equals 1. That's like the point, is that it's not like that here and here, right? The 1 is not, a positive 1 is not isolated here in these 2 equations. It's just a different relationship, right? It's very, very similar, of course, but they're different. And you could definitely construct these from scratch using a triangle. I just it just didn't feel right because the way I actually did it as a student and the way I still remember, I don't build the triangle. I just manipulate, because this one I've committed to memory, like could never forget this even if I tried. So I know that I can always work from this to build the others. Okay, let's talk about the next set of identities, which are a bit easier because we've already talked about these, the even-odd identities. Not only have we already talked about them, but there are a lot. Oh, shoot, I'm sorry, 1 second. I'll be right back. Sorry. More cat shenanigans. Oh my goodness. Okay, so anyways, why are these easier? Well, just because they are easier to write down. Sine takes in negatives and spits them out on the outside. So we've talked about that. Cosine takes in negatives and just absorbs them. So cosine is an even function. Sine is an odd function. Cosine is an even function. And what else can I say here? Tangent is also an odd function. They don't list them in the text, but since sine is an odd function, that means that we know that what's the reciprocal of sine? Well, it's cosecant. So cosecant is going to behave the same way. Cosecant is going to be an odd function. And secant is going to behave the same as cosine. It's going to be an even function. And tangent is an odd function. Cotangent is going to behave the same way. It's going to be odd. Whoops, that's x in there. I put t by accident. That's x. Okay, there's our even odd identities. I don't want to spend too much more time on this. This will come up. The problems where this is going to come up, at least in this section, it should be fairly clear because you're going to see negatives as inputs into the functions, and that should be like your key, or your cue rather, to do something with that negative that's stuffed inside of the function, whatever the function might be. All right, now we have cofunction identities. Cofunction identities. This is just relating, yeah, I've pointed this out several times, especially on the graphs, that sine and cosine are related to each other just by like shifting, right? And that's the same goes with tangent, cotangent, and secant, cosecant. So how exactly do we write that down? Well, we write it this way. It's a little bit different to how we might discuss it as a horizontal shift. It still is a horizontal shift. It's just, it's phrased a little bit differently in here. I want to explain this one in a bit more detail, and then I'm going to write down the rest because they all follow this pattern of pi on 2 minus x. This is not the way we would describe it, right? We like to have x up front and have stuff added or subtracted to x because it's less complicated. This, and what I'm talking about the context of transformations of functions, right? We know that if we subtract pi on 2 on the inside from x, then that results in a shift to the right. So, but this is like not that, right? It's pi on 2 minus x. So let's clean this up and see if we can make sense of this. And I'll sort of explain this in terms of what we like to see. So first of all, flip it around, get that x up front. Okay, I'm going to work this way. Okay, all right. Now what? Now, pull a negative outside of the sine function. Well, first, let me do this first. Just sine of negative. I'm pulling a negative off of these two terms to make that x positive. So I'm getting this. Okay, so just pulled a negative off of x and the positive pi minus 2. Oops, the negative's right there. Now I'm going to pull that negative outside. What does a sine function do with a negative input like that? You can throw it outside. So I've got negative on the outside and then x minus pi on 2. And that is equal to cosine of x. Now this is more familiar because now we see, okay, they're saying if I take the sine function and I scoot it right by pi on 2, and then I flip it over the x-axis, I'll get cosine of x. So just recall that's like some review from section 2.6 about these transformations of functions. A negative on the outside means flip it over the x-axis, and a minus pi on 2 inside the input of the function here results in a shift to the right by pi on 2. And apparently if you do those things to sine, which we could easily show by drawing it, and maybe you can even picture it, you end up right on top of a cosine graph. You know, it's an easier way to say it, honestly, is just to say that, so I'm not saying that this identity is wrong. This is how all the cofunction identities are going to be written. I'm just trying to connect it back to how we were talking about it before. But remember that the thing I pointed out is that if you just take that sine function and scoot it to the left by pi on 2, then you don't have to then flip it over the x-axis, right? So, wait a second. Let's go look at Desmos. I feel like I am going crazy. Let's see. There we go. Oop. Let me maximize this. So let's actually look at this. So we have sine of pi over 2 minus x. That apparently should be cosine, and it is. It is. And now I'm also saying that we can do it. We can write it as negative sine of there it is. That's the one I've written there. And now if I take, so all of these are the same, but I'm also saying, oops, if I take the sine function and just scoot it to the left by pi on 2, also the same. So what's the point? What's the point I'm trying to make? That you can do all sorts of different transformations to get these functions to line up with each other because they're already so similar, right? They're already so similar. The only reason that they all tend to be written in this form is because, why is it? Because all of the relationships, when you write them in this form between all the different cofunction trig functions, you know, sine, cosine, secant, cosecant, tangent, cotangent, they can all be written very cleanly in this same form. So, and that's not true, you know, or I mean, they can all be written in that clean form. And this whole thing where I can clean it up and just write it like this is only going to be true for the odd functions. So you might say, well, this is so much easier to think of, right? Like instead of all this junk where you have to figure out what this is doing to the function, this is so much easier and it works. Why not just use this? Well, because cleaning it up like this only works for the odd functions. You'd have to do something different for the when you're talking about the even functions. Like if I want to relate cosine to sine, I want to say, what do I have to do to cosine to make it match with a sine graph? You know, so that's kind of the motivation for writing them all like this. So with all that being said, that's enough background there. Let me write down the rest of these. Let me get situated back where I was with my screen and everything. Let me write the rest of these cofunction identities. We have cosine of pi on 2. See, look, it's going to be exactly the same. They're all going to have that input of pi on 2 minus x. And then we have tangent of pi on 2 minus x is equal to cotangent. And then cotangent of pi on 2 minus x is equal to tangent. See how this form, this pi on 2 minus x, can be used over and over again for all of these functions. That's why it's superior for writing out as a list of identities. Are there more clean, more, not clean, but like simpler ways to write down these relationships for these functions? Yes. But this form is going to work for all of these, which is kind of a really nice thing. Here we go. So here's how we relate the functions, the trig functions, to their cofunctions. So just in case that's not clear, the sine function is a cofunction to cosine and vice versa. The tangent function is a cofunction to cotangent, and the cotangent is a cofunction to tangent. And the same relationship holds for secant, cosecant, cosecant, secant. All right. Now I think we are ready to start running examples. We set it all up. So this is how we're going to do this. You're going to have your identities all written down on your notes as you follow along here, as you follow along with these examples. So here's example 1. Simplify the expression. So we're going to try and figure out which identities should we use to simplify the expression. Cosine of, now they go back to t, okay, cosine of t, I'm following along in the book here, plus tangent of t times sine of t. This is not an equation, it's an expression, right? No equal sign, just an expression, and all I'm doing is asking you to simplify it. What do I mean by simplify it? Well, what I mean is this is going to clean up really nicely somehow, probably compact all the way into a single trig function. So how do we do that? A good technique is to write everything in terms of sines and cosines. Put a colon there. So obviously cosine is already written as a cosine. Now here comes tangent. Tangent is the same as sine over cosine. And now I've got that extra sign attached here. So you see I've written that tangent as sine over cosine. Now I'm going to do some cleaning up. I'm going to say, okay, that's the same as cosine of t plus sine squared of t over cosine of t. Now what can I do? Can these cosines cancel? No, because of the operation of addition there. So what can I do next? And I'm going to start working a little bit more horizontally to use up this white space over here. I'm going to get a common denominator of cosine so that I can then combine these two. So I'm going to say cosine squared over t over cosine of t. There's getting my common denominator of cosine here. My right-hand fraction doesn't change. It already had that denominator of cosine. And I've scaled this one up over here, multiplying by cosine in the top and bottom in order to make it have a common denominator of cosine of t, common denominator with this fraction over here. My next step, I'm going to push these together and say cosine squared of t plus sine squared of t all over that one denominator, cosine of t. So just all I did there was push the fractions together. Now I recognize that sine squared plus cosine squared, or cosine squared plus sine squared, that's equal to 1 by my Pythagorean identity. So I have 1 over cosine of t. What's 1 over cosine of t, though? Secant. That's how this goes. You start off with some bigger expression, write it in terms of sines and cosines. Typically, that's a good first step. Maybe get some common denominators, simplify some stuff, apply some identities as necessary. Like here, when I apply the identity in the numerator to simplify this as just 1. And then finally, cleaning it up with a reciprocal identity here to get a final single term here. Cleaning it all the way up. All right, let's try another one. Okay, let's simplify this expression. So it's already written in terms of sines and cosines, so what can my first step be? Well, common denominator. That's going to be a good first step here. So I'm going to get a common denominator, and I'm going to write that explicitly here just so you can really see where the common denominator is coming into play. So I'm going to leave a little bit of space here so I can write this next step. So I'm going to get a common denominator here. And since these have no common factors, I have to basically introduce the entire denominator on both of these. So in other words, if I want to make a common denominator here, I'm going to have to give this one this factor. So I'm going to have to give it a cosine of theta in the top and bottom. And I'm going to have to give this fraction over here this entire denominator. So I'm going to introduce that here, 1 plus sine of theta. So now my new denominators will be cosine theta times 1 plus sine theta. And should be the same over here, cosine theta. So they're common denominators now. What are the numerators going to look like? Well, on the right-hand side, I've got cosine times cosine. That's going to be a cosine squared. Oh, by the way, again, we changed, I'm following the book, and again, they changed input variable. They changed that back to theta. Anyways, okay. Here in the left-hand side, I'm going to distribute sine theta to 1 and sine theta. So I have sine theta times 1 is sine theta, and then plus sine squared theta. So that's just coming from this left-hand side, distributing. Why didn't I distribute in the numerator or the denominator yet? Well, I mean, I can, and I probably will. But let's see where it goes first. Let's see where it goes first, because maybe I shouldn't distribute yet until I see if I can cancel one of the factors in the denominator. First, I'm going to push those fractions together. These are kind of fun, I think. I don't know, it's like a puzzle. All right, now I'm going to say this is the same as, do you see what I should do here? You should, if you're seeing sine squareds and cosine squareds, you should be noting that Pythagorean identity, right? This part, sine squared plus cosine squared, is just equal to 1. So sine theta plus 1 over the same denominator. This whole, these two terms together turned into a 1. And now you see sine theta plus 1 in the top and bottom, since they're exactly the same. There. So if you like, you can even wrap it in parentheses if it makes you feel better. We can cancel them, and I'll be left with 1 over cosine theta. And again, that ends up being secant theta. So just coincidence that they ended up being the same solutions here. Okay. Okay. So what can I say about this? Your algebra has to be good, right? You've got to remember that you can like cancel fractions like this. Your fraction work has to be good, right? You've got to be able to get common denominators and stuff like that. So just make sure if that's what's messing you up here, then you may want to review, or just make sure that as you're doing these problems, just consciously note where you're getting a common denominator, where you're canceling factors, where you're using identities. Maybe it'll help to write down those steps in between each step, writing down what you're doing. That might be helpful. Okay. Okay, so how do we prove, if we're given an identity, how do we prove it's true? That's going to be the next set of examples here, the next chunk of the lecture. Well, how do we show an identity is true? So we're going to talk about that. But first, let me point out that how do we show an identity is not true? Let me show you an example of that. How do we show an identity? Because this will be a much faster discussion. How do we show an identity is not true? Well, consider some identity, sine of x plus cosine of x is equal to 1. Now, this is not an identity, right? I'm about to show that it's not true. How do I show it's not true? All I have to do is find some values that will mess this up. Because if it's an identity, it's supposed to be true for all x. So let me pick x equals pi on 4. Then sine of pi on 4, supposedly plus cosine. In fact, maybe I should write a little question mark there because I'm trying to show that it's false or true. And I know that this is false, so I'm proving that this is false right now. Sine of pi on 4 is square root of 2 over 2. Cosine of pi on 4 is square root of 2 over 2. Is that equal to 1? Well, no, because that's square root of 2. Right, square root of 2 over 2 plus square root of 2 over 2 is going to be 2 square roots of 2 over 2, which cleans up to square root of 2, which is not equal to 1. So how do you show an identity is not true? You just find some value that breaks it. But how do you show an identity if it is true? How do you show an identity is true? That's a bit trickier. Oh, there we go. What you're going to want to do is work each side. Well, there's a few techniques we can use. We can work each side individually. That's one technique. But the other techniques are really coming back to the same things that we use to simplify expressions, which are to write things in terms of sines and cosines, and to use the identities that you know, like the Pythagorean identity, reciprocal identities, etc. So let's do an example. I think that's going to be the best way for me to show you what's going on here. We'll actually do a few examples. So let's consider the equation cosine of theta is equal to secant of theta minus cosine of theta should be equal to sine squared of theta. Now, what's the question? Because that's the identity. The question is, or the instruction is, verify. I'm following the example in the book. Part B says to verify. Part A says to verify algebraically, which is what we're going to do. Part B says to verify graphically. That means literally plug it into Desmos. I guess I could do that too. But really, part A is the point of this example. All right, so here's what I do. First of all, let's get on the same page with naming the sides of these equations. I'm going to name this side, the right-hand side, and this side, the left-hand side. Okay, and I'm going to denote that by LHS if I need to write it down. Left-hand side, right-hand side of the equation. All right. Since there's more going on over here that I can work with, I'm going to work with this side. I'm going to put an equal right down the middle. And I'm going to say, okay, what can I do here? I could go ahead and distribute the cosine, or what I'm going to do is first write the secant in terms of sines and cosines. And what is that relationship for secant? It's 1 over cosine. So let me clean that up first. And that's still equal to sine squared. I'm going to write another equals, write down, lining them up vertically. Now I'm going to distribute the cosine. What's cosine times 1 over cosine? Well, just 1, right? So that's 1, and then minus cosine squared theta. And at this point, I would say that this is true just by working the left-hand side, because I know from the Pythagorean identity that cosine squared theta plus sine squared theta is equal to 1. So if I manipulate this and subtract the cosine over, I'm getting 1 minus cosine squared theta is equal to sine squared theta. So at this point, you could stop right there. And I didn't have to do anything to the right-hand side. That's going to be how these go. Sometimes if there's more going on one side or the other, you have more to work with. And often you can just carry down that other side, work with, one of the sides, and eventually you get it to match. Sometimes both sides will be complicated and you've got to get them both to work to like a common ground. We'll look at one of those too. Part B says to verify. So this is verify that this is an identity. We're doing this algebraically. That's what I want you to be able to do. Verify graphically. I'll show you that real quick. That literally just means go pop it into Desmos, though. I'm just going to say verify graphically. And I'll just say Desmos. Because you cannot be expected to know what this graph looks like, right? Or even sine. We haven't even talked about sine squared, but Desmos knows what it looks like. So let's go use Desmos and say, first of all, we have sine squared of x. Okay, there's the sine squared of x function. Sine squared. Which is interesting. It's like a sine graph, but it's all positive, right? Because that's what squaring something does, is makes it positive, or that's one of the things it does. Now we have cosine x times secant x minus cosine x, and there they go. Nope, wait, it doesn't like that. Why doesn't it like that? All right, it wants me to use parentheses around the arguments of these trig functions because it got a little confused. There it is. They are, in fact, equal because they're right on top of each other. Okay, cool. That's all you have to do to verify it graphically. Just plug it in into Desmos. All right. Let's do another one. Let's not do that graphing thing again. That graphing, I mean, what I need you to be able to do is to do this algebraically. Verify the identity. Now this one is going to look a little bit different. Let's say 2 tangent x secant x equals 1 over 1 minus sine x plus 1 over 1 plus, oh wait, hang on, that's minus in the middle. That's minus 1 over 1 minus sine x minus 1 over 1 plus sine x. All right. So here's what I'm going to do. I'm going to label this over here left-hand side. Okay, so now I'm only taking the left-hand side. I'm going to take this over here. I'm going to work it a little bit differently than I did the previous one. The previous one, I just carried down the right-hand side as I worked the left-hand side, but I see both of these are a little bit complicated, especially this one, and I don't want to have to keep writing it over and over again. So for the sake of organizing my work, I'm going to have left-hand side. I'm going to work it a bit, and once I reach like some point that seems natural to stop at, I'll go work the right-hand side. All right, so let's write these in terms of, let's see, where do I want to put a line down the middle for right-hand side. Okay, I'm going to write these in terms of sines and cosines. So I'm going to say 2 tangent is sine of x over cosine of x. Secant is 1 over cosine of x. Okay, cleaning this up, I've got 2, multiplying the fractions, times sine of x over cosine squared of x. And at this point, like, what else could I do? What else could I do? I know I can write cosine squared in terms of like ones and sine squared from the Pythagorean identity, but maybe I'm not sure. Like, should I do that? I don't know. Let's go work the right-hand side. 1 over 1 minus sine x minus 1 over 1 plus. So I'm going to have to find a common denominator here by multiplying. I'm going to have to give this one the 1 plus sine x in the top and bottom. I'm going to have to give this one the 1 minus sine x in the top and bottom. So if I go ahead and write the fractions squished together, my denominator should be 1 minus sine x and 1 plus sine x. And in the top, I should have over here, I'm giving this 1 plus sine x over here, so 1 plus sine x, just multiplying that by 1, and then minus, and then this one got multiplied, 1 minus sine x got multiplied over here in the top and bottom. And since I'm subtracting the entire fraction, I need to make sure that I wrap it in parentheses, and I'm going to say 1 minus sine of x. That's very important that if you're subtracting an entire fraction like this, and then you get a common denominator and you stuff the fractions together, you've got to remember to write that that part up here, the part you introduce over here in parentheses, so you remember to subtract both of the terms. So I encourage you to write out all the steps to get from here to here, write all the fraction work, right? Just to make sure you're good with your fraction work. And if this makes good sense to you, though, if you can jump straight to this step, then that's that's where you want to be here. Okay, so now in the top I have 1 minus 1. That's going to cancel. You see that? 1 minus 1. And then I have sine x minus negative sine x. Long story short, I get a 2 sine x. That looks good. 2 sine x. And in the bottom, what do I get? Let me actually go ahead and multiply this out. 1 times 1. So I'm going to do 1 times 1 is 1. 1 times sine x is sine x. Now moving on to negative sine x times all these in here. Negative sine x times negative sine x times 1 is negative sine x. Negative sine x times positive sine x is negative sine squared x. Oh, by the way, these are equal to the original. All right, obviously. And then I have 2 sine x over 1 minus sine squared of x. The central terms cancel, right? You may have already recognized this as a difference of squares. You may have already noticed that. Or this is a difference of squares, and this is the factored version of a difference of squares. All right. Now, the last thing I should do is over here, since it's a bit easier, I have more room to work here, but you see they are the same now. The only thing I maybe should do is like stuff that 2 up top, just to make it like explicitly clear that these are the same, but obviously it doesn't matter where the 2 is. It can be out here or up top. It's not in the bottom, right? All right, and cosine squared is equal to 1 minus sine squared by the Pythagorean identity. Just subtracting sine squared, scooting that to the other side. And then now I have the 2 sides being equal. Let me get that all on one page there. It's tricky. The side's tricky, right? I'll try to work this problem again on your own. It's a good one to try. Now let's do another tricky one. So you're going to see when you're working the homework for this section in WebAssign. I need to find some problems. I'm going to give you problems to mark for review later on. I'll probably give them all to you at once, like I did for exam 2. But when you're working the actual WebAssign homework, not the review problems from the text, but the WebAssign homework, you'll see that I'm going, as I often do, a bit more intense in the lecture than the homework or exam will be. So they're using U as their input letter now, the letter U. They're just trying to mix it up on you. That's all. All right, and this is equal to. So, I'm almost out of room, plus tangent of U. This is example 5 in the text. You see something, hang on, why is my, okay, all right, let me rewrite this. Cosine of U over 1 minus sine of U equals secant of U plus tangent of U. There we go. So yeah, as long as you can do the examples, or rather the WebAssign homework, you'll see that they're a lot less intense than these, or example 4. As long as you can do those, then you're in good shape. But I like to show you the harder ones, just in case you ever have to deal with them. All right, so let's work the left-hand side. We'll split it up again, and right-hand side. So my left-hand side, I'm starting with cosine of U over 1 minus sine of U. What can I really do with that? What can I do with that? Maybe you're not sure, right? Maybe you're not sure. So let's go look at the right-hand side. Secant of U plus tangent of U can be written in terms of sines and cosines as 1 over cosine of U plus sine of U over cosine of U. Oh, that's already got a common denominator, so this is the same as 1 plus sine of U over cosine of U. Whoa, so what's going on here? Because this is like almost the opposite, right? It's like flipped upside down. So what's happening? Okay, what we have to do here is we have to get creative, and we have to introduce this factor. So you may recall from 112, whenever you were dealing with rationalizing denominators when you've got like something like 1 minus square root of 2 in a denominator, then you multiply by its conjugate. That may ring a bell. We're going to do a similar thing here, where we're going to multiply by 1. So something in the top and bottom that's the same. So technically just multiplying by 1, but I'm going to multiply by 1 in the form of 1 plus sine over U, 1 plus sine of U over 1 plus sine of U. So this is a legitimate thing to do because all I'm doing is multiplying by 1 because it's the same in the top and bottom. Why would I ever want to do this? Well, because it's going to clean up my denominator quite a bit. Because remember, this is the same denominator I had back here from example 4, and it cleans up to just 1 minus sine squared of x. 1 minus sine squared x. So that denominator is 1 minus sine squared of U. In this case, it's the variable U. By the way, I keep forgetting to write equal signs here. This is equal. Okay. 1 minus sine squared U. And in the top, I have cosine of U times, I won't distribute it yet. Cosine of U times 1 plus sine of U. So I'm not distributing yet. Okay, what happens next? I'm just going to rewrite my numerator because now I'm about to mess with that denominator. Recall that denominator, 1 minus sine squared, 1 minus sine squared by the Pythagorean identity is cosine squared. That's like a popular little technique we're using there where you have 1 minus sine squared equals cosine squared. Or we use the other one for a different example where it was 1 minus cosine squared is equal to sine squared. So recall that that can be used, that Pythagorean identity can be used in that way. And now, cancel a cosine. There's a cosine up top, two cosines in the bottom. So now I'm just left with 1 plus sine of u over cosine of u. That's one of the trickiest ones because you have to introduce that multiplication up there. Whoops, there we go, of this term. That's one of the trickier ones for sure. Okay, two more examples, and that'll be it for chapter, or not chapter, but for section 7.1. So example 6, just another verification, just practicing using these identities and algebra techniques. I'm just going to say verify 1 plus cosine of theta over cosine of theta is equal to tangent squared theta over secant of theta minus 1. Cosine of theta, wrapping all the arguments for these functions in parentheses. There we go. All right, let's work that left-hand side and right-hand side separately again. Left-hand side is 1 plus cosine of theta over cosine of theta. What can I do there? Well, look at this. I can split the fraction into I can split the fraction into two pieces, 1 over cosine theta, 1 over cosine theta plus cosine theta over cosine theta, just splitting that fraction apart using the same denominator, right? Cosine theta, just splitting it around that plus sign. The opposite of that step I do where I squish the fractions together, doing that in reverse, tearing it apart. What's 1 over cosine of theta though? That's secant of theta. So it's not always a bad idea to go back to secant, tangent, cosecant, or cotangent functions, especially if your other side of your equation involves those, right? Now here, what's cosine over cosine? That's 1. So can I go any further with this? Probably not. Let's see what I can do with the right-hand side. Tangent squared of theta over secant of theta minus 1. Could write these all in terms of sines and cosines, but anytime I'm seeing squared trig functions, I should immediately be thinking about those Pythagorean identities. And if I go look at them, which one am I going to use? Well, of course, I'm going to use this one that involves tangent. It says that tangent squared will be equal to secant squared minus 1 if I subtract the 1 over, right? Just manipulating the identity a little bit. So that means I can replace this tangent squared here, tangent squared theta, with secant squared theta minus 1. Copying over the denominator. Okay, so now what I can do is I can say, oh, look, that's this secant squared theta minus 1, that's a difference of 2 squares. Right, got to recognize that. That's a difference of 2 squares. Remember, a squared, we've seen this a few times today. A squared minus b squared is the same as a plus b times a minus b. Now, the few times we've seen it today have been going in the opposite direction, multiplying two, like 1 plus sign, 1 minus sign, giving me 1 minus sine squared. We've seen that twice today, but now I'm going the opposite way. I've got this form, that's difference of squares, and now I want to factor it. So I'm going to have secant of theta minus, well, I'll say plus 1, and then times secant of theta minus 1. And you see why I wanted to do that. right? Because it's going to cancel this factor secant of theta minus 1 is going to cancel with this factor secant of theta minus 1 in the denominator. When those cancel, I'm just left with secant of theta plus 1 because these completely go away. And of course, that's it. Right? Those are equal now. Okay. Example 7 is they title it trigonometric substitution. This is going to be real good for you if to see now if you are going to go on to take the calculus sequence. This will come up. So it says to substitute sine of theta for x in the expression, and then I've got an expression involving x. Square root of 1 minus x squared. And simplify, of course. And also we're assuming that theta, for details, we're not going to worry about, that theta is between 0 and pi over 2. Well, okay, really, I'll explain why that is when it comes up. Okay, because it's not that difficult. Okay, so 1 minus x squared, it tells us straight up what to do. It tells us to plug in sine theta for x. So I'm going to have 1 minus sine squared of theta. 1 minus sine squared of theta. But I know that by my Pythagorean identity, that's the same as just cosine squared of theta. Right? I've used that several times today, right? This manipulation of the Pythagorean, just by subtracting sine squared over, I see that cosine squared is equal to 1 minus sine squared. And then finally right here, now you know that when you take a square root, you got to be real careful about whether it's outputting positive or negative. But that's why we assume that theta is only between 0 and pi on 2, because that means that cosine of theta is always positive for theta between 0 and pi on 2. That's why we're doing that. So we don't have to worry about the like plus or minus on the square root or any of that nonsense. So this just ends up, you get a square root of a squared thing. So this just ends up being cosine of theta. So this seems kind of weird and out of place here, but it will. This will come up. Things like this will come up when you do trig substitution in when you're dealing with integrals involving things like this, which makes no sense to you right now, but it will later. All right, that is it for section 7.1.